Welcome to Organic Chemistry. This video focuses on infrared spectroscopy. Let's get started. Now, recall that across the electromagnetic spectrum, different wavelengths interact with molecules in different ways. Radio waves translate molecules, microwaves rotate, infrared vibrates. Of course, visible and UV light excites electrons. So when molecules absorb infrared radiation, the energy goes directly into bond vibration. Any molecule with an n number of atoms in 3 dimensions has 3n total modes of motion. 3 of those are translational and 3 are rotational. Everything else is vibrational. And it's these vibrational motions that IR spectroscopy detects. Incredibly, the physics that we use to describe springs matches exactly to what goes on when molecules absorb IR light and vibrate. When two atoms are bonded together, they behave almost exactly like two masses connected by a spring. If the atoms move closer together, repulsion increases. If they move farther apart, attraction decreases. So the bond oscillates between compression and extension, storing and releasing energy. It is just like a spring, and energy moves back and forth between potential and kinetic energy. And just like many physical systems, this vibration follows the mathematics of simple harmonic motion. If we set the restoring force of a spring equal to the motion of the masses, we get a familiar second order differential equation for oscillation. The important point here is not just the calculus, but that bonds vibrate at specific natural frequencies. And these frequencies depend on really two things: how strong the spring is, or how strong the bond is, and how heavy those atoms are. Now, in real chemical bonds, this involves two atoms. So the vibration depends on both of those masses. When we solve the equations for two masses connected by a spring, we obtain what's called the reduced mass of the system. That reduced mass determines how quickly the bond will vibrate. The final result is beautifully simple. Vibration frequency depends upon the strength of the spring, the strength of the bond, and their atomic masses. And now we bring in light. This is the only time we're modifying this equation to bring in the frequency of light. And infrared radiation can excite these vibrational motions. But there is an important requirement. For a vibration to absorb specifically infrared light, that vibration must change the dipole moment of the molecule. The dipole requirement determines whether the vibration can couple to the electric field of infrared light. If the vibration changes dipole moment, the oscillating electric field of that photon can interact with it. If the vibration does not change the dipole moment, the electric field has nothing really to push on. The vibration still exists, it just cannot absorb IR radiation. And so that's why we will focus here on bonds like oxygen single bonded to hydrogen, or nitrogen single bonded to hydrogen, or even carbon double bonded to oxygen, where they give very strong IR signals. And now we can get the whole perspective. Different types of bonds absorb IR radiation at very predictable frequencies. We can understand these trends directly from the physics. Stronger bonds will vibrate faster, while weaker bonds will vibrate slower. Lighter atoms also will vibrate faster, while heavier atoms vibrate slower. You can see triple bonds absorb higher frequencies than double bonds. And double bonds, of course, absorb higher than single bonds. But all bonds involving hydrogen, the smallest atom, appear very high on the spectrum because hydrogen is so light. So here we have our instrument, an IR spectrometer. It shines infrared light through a sample and measures how much light passes through. What is plotted on the spectrum is transmittance. So when you see a dip in the graph, that means the molecule absorbed that frequency of infrared radiation. Each dip corresponds to a specific bond vibration. When reading an IR spectrum, we don't try to identify or interpret everything at once. Instead, we follow a simple strategy. First, identify the carbon single bonded to hydrogen bonds. sp3 carbon single bond hydrogen bonds appear around 3000 to 2850 per centimeter. These peaks are often strong because organic molecules contain many carbon single bonded to hydrogen bonds. You'll also notice that the more complex molecules produce more peaks in the fingerprint region. This is below 1500 because there are simply more vibrations occurring. But now we distinguish the type of carbon single bonded to hydrogen bond. sp3 C to H appears below 3000, while sp2 C to H appears slightly above 3000, and sp hybridized C to H appears near 3300. This happens because increasing S character strengthens the bond, which increases the vibrational frequency. So hybridization directly affects where the peak appears. Next, we check for our O single bond H or N single bond H bonds. O single bond H bonds stretches appear around 3,500 to 3,200 wave number, but they are usually broad. That broadness is caused by hydrogen bonding between molecules. Hydrogen bonding weakens and lengthens the OH bond slightly, which spreads the absorption across a range of frequencies. NH bonds appear in a similar region but tend to be sharper. Primary amines show two peaks, while secondary amines show one, and tertiary amines, of course, would show none. Hydrogen bonding also explains why spectra look different in different phases. In the gas phase, molecules are mostly isolated, so peaks are narrow and sharp. In the liquid phase, however, molecules interact with each other, especially through hydrogen bonding, and those interactions broaden the vibrational energies, producing broader peaks. Finally, we look for carbonyl groups. The C double bond O bond produces one of the strongest and most diagnostic signals in IR spectroscopy. Most carbonyl stretches appear between 1850 and 1650 wave number, but different carbonyl functional groups absorb at slightly different frequencies. The reason comes down to how electrons are distributed around the carbonyl. Amides at the top left appear low, around 1650, because nitrogen donates electrons by resonance, weakening the C double bond O bond. Conjugated carbonyls appear around 1680 because pi electrons are shared across a larger system. Simple ketones appear around 1720, where the carbonyl is localized. Esters, lower left, appear slightly higher because oxygen withdraws oxygen electron density inductively. Acid chlorides appear even higher due to strong inductive withdrawal. And finally, acid anhydrides show two peaks because the two carbonyl groups vibrate together in symmetric, lower energy, and asymmetric, higher energy modes. So the position of an IR peak ultimately comes down to a number of physical ideas. Resonance pi donation delocalizes electrons and weakens the localized bond, lowering the frequency, while inductive withdrawal pulls electron density away and strengthens the bond, raising the frequency. Infrared spectroscopy is therefore measuring something deeply physical, the strength of the bond, quote-unquote, spring connecting the atoms. And by reading these vibrations, we can identify functional groups present within a molecule. Till next time, Crip.